Okay, now let's understand some of the different ways how m values are initialized. These are also the same methods that are done on neural networks. Okay, first it could be zero initialization. First they start with zero value, and slightly if they are starting with zero value as m, then the next step immediately is to increase the value of m. Okay, this is why I was saying sometimes they increase, sometimes they decrease. If they start with zero initialization, they'll slowly start increasing the m value until they get to the um, losses or the residuals or the errors between predicted value and the original value are minimum. Okay, second method is random initialization. In random initialization, okay, you start with very small value and from there you keep on, again depends on the range. Okay, so from there you can continue to start decreasing the values. Okay, so various pros and cons are mentioned. In the first method it is simple and quick, but it will take a lot of time because you have to keep on adding the values. Second method is it improves the variability. That means it improves, it is applicable for various use cases. Okay, because the model is exploring parameter space, but then there is poor initial performance. So that's why when you run a neural network model, in the very first epoch, loss is huge, accuracy is low, and slowly it starts increasing. That is where I think they are using random initialization. Another method is Xavier initialization, or also called as GLOROT. Okay, in GLOROT method, what they are doing is they are using a distribution. So they are taking into account mean as well as variance factors. Okay, so they use this formula variance 2 divided by number of inputs and number of outputs, and basis on this they initialize the parameter value. So this is another method. So this method advantage is it's a good balance between input and output layers, but the problem is it requires in-depth knowledge of layer size and how much to add and all of that. More like it's more like experimental method. Okay, next is HE initialization, very similar to Xavier initialization, but here what they do is that instead of taking 2 divided by n number of inputs and outputs, they rather take square root of 2 divided by number of inputs, and this is mainly used for ReLU activation. Okay, so there for ReLU activation they have to use m values, right? To calculate m values they make use of these methods. Okay, and this helps in solving one of the major reasons why we have something called vanishing gradient problem. So that is a very big interview question if you talk about neural networks. So that is how it is solved. How it is solved is they use HE initialization by making use of scaled some values. Okay, number of input values by taking square root of 2 divided by number of input values for layers for calculating m values. Okay, for initializing m values, slope values, and this solves another big problem called vanishing gradient problem, and this is mainly applicable for ReLU only. Okay, that ReLU activation function. We'll talk about all of this, but I'm just giving you just some foundational knowledge so that you can understand there are different ways of initialization of m values. Another one is LeCun initialization, named after the data scientist himself. So parameters are used initialized using normal distribution. Here instead of 2 divided by number of inputs, we take 1 divided by number of inputs. It works very well for tan activation function, tan h activation functions, and preserves the variance, and the same disadvantage as HE initialization, it works only for tan h. And next is variance scaling initialization, just to initialize the m values. So all this thing in all the layers. So this is another method. So where you take into account variance remains constant. So again it helps in solving input signals variance problem. Okay, but then the problem is if you change the architecture, that means if you add more layers of neurons or decrease the number of layers of neurons, you will have to tune it again. Okay, so different ways of initialization of m values. Anyway, so moving on to back to the matter, back to the topic in hand. What are the assumptions of logistic regression? Basically, we are expecting a binary outcome most of the time. Okay, that is the first assumption. So logistic regression has to be used for binary classification only. But if at all you have multiple classification, there you will have to change multi underscore class parameter to multinomial or OVR. How they work, that we will talk in next class, but you can do that also. Next is independence of observation. So all the rows, observe, when they say observation, we are talking about rows. Okay, rows of data. So all your rows should be independent. They should not have some dependency of one should not be there on the another. For example, for loan approval, let's just say father applied for a loan, so did the son. Okay, father applied for the loan, and in the same data set son also applied for the loan. Now there is a dependency. What is the dependency? Their CIBIL scores might be, no, not CIBIL scores, family members may be same, number of assets could be same, number of sometimes they also take into account which area the people are from. Now it's a banned practice, banned by government. But then previously that used to happen. Only certain people from certain areas who were getting loans. Okay, so that also was a parameter. So anyway, so there is some dependency between the rows. So such thing should not be there for logistic regression. Okay. Next thing is linearity of logits. By logit you mean probability, and this you will get to know only after using the algorithm. Okay, after using the algorithm, your y-pred values, when you do, okay, let me show you here. So when you do this predict, right, you also can run predict probability. You also have a method called, if I run here model dot, this one, pred underscore proba. Pred underscore proba will give you the probability. Okay, here predict will give you the classes, which class they belong to. Predict proba will give you the actual probability basis on which the decision was being made. Okay, now what we are saying is these probabilities should be linear. They cannot have non-linearity between them. Okay, it makes sense also. Why? Because your sigmoid function takes linear values only. If it is quadratic or logarithmic, you have to transform and then pass it to sigmoid function. Okay, so this makes sense. These logics should be linear, and I think they will be linear. 99% of the cases they'll be linear. We don't have to worry. Next is no multicollinearity, same as linear regression. The individual columns that you have here, okay, they should not be predicting the same thing. For example, they should not have some sort of correlation between them. For example, let's just say pressure and humidity. PV equals to RT, right? So pressure and volume are dependent, and they are also dependent on temperature. Temperature increases, pressure decreases. Sorry, they are directly proportional. Pressure increases, okay, temperature will increase. If temperature increases, pressure also increases. So that way. Anyway, this applies for gas, but I'm just trying to come up with, give you some sort of explanation here. So basically, some of these columns may have dependency, may have correlation. If one increases, other may increase. Such columns cannot be considered, okay, for logistic regression, same as linear regression. And then logistic regression, in order to do the M calculations, in order to give you the best results, you need to have large sample size. Okay, if you have only 10 rows of data, you can't do anything with logistic regression. No need to even apply. You can manually maybe multiply with mean and get the results. Okay, that you can do. 10 rows, 100 rows is like too less of data for logistic regression. Next is absence of outliers. Oh, because you're talking about straight line, okay, line is being considered, okay, in order to calculate M values, and that line itself is being passed to sigmoid. Okay, so that's why outliers will change the direction of that line. if m value changes, okay, I think I forgot to show you. This is the logistic equation. Okay, so this is the original equation for logistic regression, but the thing is numerator is 1 for us, so c value should be 1. This becomes 1 divided 1 plus a value should be 1. A value make it to 1. Okay, 1 divided by 1 plus e to the power of x or e to the power of minus x, actually, to be honest. So k value again has to be 1. Okay, k in this equation, original equation, c is 1, a is 1, k is 1. Now when you substitute those values, this becomes sigmoid function. You can modify. If you modify, you can see how various things affect. Okay, but usually see numerator is 1, so upper value is 1. That's why if you notice, this is 1, the highest range that you see here, this is 1. So it will give you value between 0 and 1 only, this way. If you want to modify numerator, it will increase. Numerator, let's not modify numerator. So this is another parameter, but this is also 1 in most of the cases for us. And k value, it depends on the equation. K value is what will, see, notice k value, what k value is doing. K value is your linear equation. K, x are linear equations here. M1, nothing but m is what I'm talking about. Mx, right? Y is, z value here is y is equal to mx. So m is k here. So if you change m, slope changes. This is the same thing we saw for linear equation also. If you change m, the whole line would change, right? So that also I think we can open. Linear regression interactive. So that also okay, takes time. Okay, so this we saw in this equation mx. If you change the value of m, okay, this way it changes m. Notice m here, this here. I'm only changing the direction of the line. M value changes. Of course, B is also changing a little bit, but then not much. But M value changes a lot. B value is B or C or in this case theta naught, C, B all mean one and the same. So theta naught represents how much it touches the y axis. Okay, so that is what theta naught is. But m values is the slope changes. So coming back to logistic regression, here k value is the m value. Notice it changes. So this is how you can modify the logistic regression. It gets calculated automatically. Now coming back, so outliers should not be there. See what is happening. I'm taking this point, I'm moving it as an outlier. This point is not following this direction. Ideally it was supposed to be like this, but now I have moved it here. Because outlier is there, m value changed. Because m value changed, your y prediction values will change. If y prediction values change, your model fails, right? Fails to do the proper generalization. So that's why even for logistic regression, m values should not be there. Okay, so that is another assumption. Next, up until this point, have you understood? All good? Give a thumbs up, that should be enough. Okay, yeah, thank you. So Mahalakshmi, Ashwin, so you are also following? Okay, all right. The next concept is, okay, very important concept, talking about, now we are going to talk about solvers. Those solvers that you saw. Okay, this is all fine. So up until this point we understood, okay, m values is being initialized by various methods like this. Okay, you are initializing m value, you are multiplying with x value, you are getting y value, which is all fine, which looks fine for us. But the problem arises at gradient calculation. This subtraction of these values that you are talking about. how to know, first of all, how to know whether to increase or decrease and how much to increase or decrease. Okay, first one we got to know. First one we saw various heuristics, random initialization, zero initialization, and HE initialization, Xavier, Glorot, whatever. So these things we understood, first point. What about the second and third point? Third point is how much to increase and how will you know whether to increase or decrease or which direction to increase or decrease. That is the next question. That is answered by your solver. That is what solver is there for. The solver that you pass, usually by default, if you see the solver is LBFGS. Okay, we will see what that is, but there are different methods also. Newton CG is there, SAG is there. SAG stands for stochastic gradient descent. Okay, Saga is there. It's a variation of again stochastic gradient descent. LBFGS is there. Okay, so all the liblinear is there. So all these methods are there in order to do what? In order to get the how much to optimize to solving the optimization part. That we will look now. But before that, you have to understand what is this Hessian matrix. How this comes into play. Okay, so we have a concept called Hessian matrix. Let me open the Hessian matrix. Okay, we have a concept called Hessian matrix. Okay, what is meant by differentiation and what is meant by integration? Integration means if you start adding small parts, minute parts, how much will they increase? That is what integration talks about. Okay, basically if you apply integration means if you integrate certain value for here from this portion, smaller portion A to upper portion, certain portion B, how much this function will differ, how much this function will increase is what integration talks about. Okay, on the other hand, differentiation, what differentiation talks about is for the same scenario, if certain function is being differentiated, yeah, let me see if I have something here that I can use. Yeah, so here let's just say this one. Okay, so okay, this is heat equation. Okay, let me give you an example, different example, and explain. I think I gave this example previously also. What differentiation talks about is, let's just say you have water pot, you have a plant in your pot, you will put glass of water to it, and 3 things or 4 things happen. One, the water that you put, 1 glass of water, some of it gets evaporated, some of it gets absorbed by plant, some of it gets mixes with the chemical which are present in the soil, some of it starts dripping, right? Some of it comes out of that pot. 4 things happen. Now what differentiation is talking about is, for the function of plant growth, if I take plant growth as a function, how much of the impact did the glass of water have? Okay, how much impact will the water have on the plant's growth, basically by taking into account four of these different scenarios. One, dripping of water, how much water got dripped, how much water got absorbed, how much water got mixed chemically, and how much water evaporated. So those things we calculated in differentiation. Okay, so for example, if you have this x sine x square plus 1, if you differentiate, x is one parameter, the equation could be much complex. X sine of x square plus cos of y square plus tan of z square, something like that. If you take only whole differentiate by only x, what we are talking about is how much of x parameter is impacting this entire process, how much of y. In this case, let me write a simple, let's just say d by dx of, not d by dx, okay, let's just say one of my parameter, I will take u, v, w, or maybe I will take t. T is for that plant growth. Let's do this in better way. Okay. dripped. Okay, water got absorbed, and then some of the water got evaporated. Okay, and some of the got mixed. Okay, now if I take f is a function or g is a function, let me take f is a function for plant growth. What we are trying to do is d of f, how much d of f is affected by various parameters. In this case, let me take d, okay, or I'll take dr for dripped. Okay, how much this dripping is impacting that function. Okay, again I'm taking df. I'll take df only. I'll remove this bracket for simplicity. Okay, how much plant growth is being absorbed by dA, absorbed. Okay, how much plant growth is being absorbed by dE, the evaporation. How much plant growth is impacting by mixing of water. So all these four calculations we have to do in order to understand the plant growth function. Okay, this is how differentiation works. But pay attention now what I'm gonna say. This is the normal differentiation. Okay, this is the normal differentiation. Now what is partial differentiation? Partial differentiation is if you take this df, okay, divided by, but you have dr also, okay, then you have dA also, sorry, yeah, you have A also, you have E also, you have M also. Out of these four parameters, how much of this function gets impacted by only one? You have to consider only one. For partial means, for full differentiation you will consider everything. For partial means you will consider only one parameter. Okay, that is partial. For partial, what I'm gonna say is how much of that df I'm gonna differentiate f with respect to dr only. How much it is getting impacted. Let's just say my equation was dr squared. Okay, let's just say for the sake of simplicity, I'm replacing x with dr because I have to differentiate with respect to dr. No, okay, sine squared plus cos of something. Actually, the plant equation is much complex, but I'm writing something randomly. Don't worry about it. Let's just say cos of absorbed, okay, plus tan of some evaporated. This differentiation, even though I have four parameters here, I have to differentiate it only with respect to dr. If I differentiate it with respect to only dr, okay, what will I get? Only this term will get differentiated. Okay, only this term will get differentiated because these are not dependent on dr. They will be retained as is. Do you agree? Okay, partial differentiation means you take an equation, you differentiate it only with respect to one parameter. This is how partial differentiation works. Okay, and second order partial differentiation means first you differentiate this one. What is differentiation of sine of x? Cos of x, right? Forgot, is it? Okay, sine x is cos x. Cos x is minus sine x. Forgot. Anyway, never mind. So if you differentiate only one term, so sine squared x is there, so you can take this as x to power of n. X to power of n is n into x power of n minus 1. So that means this will become, okay, 2 cos x or something. Okay, so 2 cos x, whatever the, don't worry about the exact differentiation, just pay attention to how what we are trying to do here. So second order differentiation means first you will differentiate once, whatever the result you will get, again you will differentiate that. 2 times you will do the differentiation. That is what is called as second order partial derivative. Okay. So second order partial derivative is, you will take a equation, you will differentiate with respect to only one of them. That's why if you pay attention here in this matrix, everything that you see in the denominator is x only, x term only. See? Okay. They are only x terms. So the point we are trying to make is, Hessian matrix is a square matrix that calculates its second order partial derivative of a scalar valued function. Ignore the scalar valued part for now, I'll explain that. So basically, Hessian matrix is a matrix, okay, which is a squared matrix, which is obtained by calculating second order partial derivative of a function. So you can throw any function at it, doesn't matter. You give it any function, mostly scalar functions only. Okay, scalar functions are the functions that are dependent on only one parameter. Okay, so anyway, so scalar valued function you give it, it will give you the second order partial derivative. Okay, but if you start plotting that, whatever the result it gives, you will get two different things. You will get functions maxima and minima. Okay, let's look at an example. So scalar functions means like this. Notice, okay, only xy terms are there. There are not much complexity here. So if f of x comma y is one equation, if you want to start calculating first order partial equation for this, okay, with respect to x you have to calculate, and then with respect to y you have to calculate. Okay, this is what partial differentiation means. X you are calculating, y you are calculating separately. With respect to x, the equation becomes 3x square, blah blah blah, and with respect to y, the equation becomes 4y cube. Okay, so when you get this, again you further differentiate this. Again you differentiate this one, you will get 6x plus 6, 6x plus 6, and this one you get 12y square plus 8. So 2 times you are differentiating. When you differentiate 2 times, you write it like this: dou square f by, or delta square f by delta x and delta y, and you will get this matrix 6x plus 6. This also you will calculate for the Hessian matrix, okay, with respect to x and y, and you will get these values. You'll mention this, and you can substitute the values of x also at certain points. At what point? At point 1 0 1 comma 0, what my Hessian matrix looks like. It looks like this. Okay, at certain other point, what it looks like? It looks like something else. So this way Hessian matrix is calculated. But the beauty of this calculation is, at each point, so after you are done calculating for various points, you will get two different things. You will get local minima and local maxima. That means basically what we are saying is, this Hessian person who came up with this Hessian matrix is a very clever way of finding out what is my lowest point in that function and what is my highest point in that function. Okay, so that much you understand for now. When you plot it finally, notice this entire cost function we have taken, the Hessian matrix calculations are done. Highest point could be here, okay, this is the upper side, or it could be here, and lowest point is this point. So this way 2 different points are obtained by Hessian, is given by Hessian matrix. Now the question is, why are we talking about Hessian matrix? What has this Hessian matrix got to do with the optimization algorithms that we discussed? We have various optimization methods: Newton CG method, Newton Raphson, Newton that is liblinear, okay, LBFGS. So all those methods are there. What is this matrix got to do with those optimizations is what we are gonna understand. But did you understand the Hessian matrix? Okay, awesome. Okay, so now taking this Hessian matrix concept, the way, see, the original question we are trying to answer is this, right? How to know whether to increase or decrease the randomly initialized values, you got it, but how will you know whether to increase or decrease? If you are increasing or decreasing, how do you know how much to increase and decrease? That is the next question. Okay, what if you take that entire cost function or loss function that you have calculated and convert it in the form of an area? One, you'll take that function, convert it into an area. Now, by application of this Hessian matrix, you will get to know where is the upper part, where is the steepest part, lowest, steep means, okay, steepest part and the highest part. What is meant by steep? Steep means the lowest part, right? So you will get to know where is the highest point and the lowest point. The moment you know where is the highest point and lowest point, what was our original aim with cost function? We had to decrease it, right? Our whole aim of using these algorithms is to decrease the cost function, decrease the loss. That is our aim. If you decrease the loss, that means y prediction will be closer to y original value, y value. That is our whole aim. Keep that in mind. Now you are taking that cost function, converting it into an area by making use of Hessian matrix, which will give you your upper point and lower point, and lower point is what we are interested in. Okay, so when it gives you the lower point and upper point, now you know which direction to go. From upper point you have to go to lower point. That is okay, that is one thing you got to know. Okay, second thing you got to know is also, you got to know both the things. Now you have to decrease from upper point to lower point. This question is answered. Okay, second question is, how much will you increase? How much will you increase is in the direction you have to flow. We don't know the exact value. Again, this Hessian matrix or any solver will not give you the exact value, how much to decrease or increase, but instead they will tell you go into certain direction, you will arrive it after certain iterations. Okay, so that is what it will tell you. Basically, first you will take the cost function. Cost function anyway you got it from the logistic regression or linear regression, that you will put it in this Hessian matrix, okay, as the value of f becomes a cost function, and x becomes slope. X is slope value. What you see here is x values are slope values. With respect to slope, you will start differentiating this function. You will get an area like this. Okay, once you get the area, let me modify here some little bit, and you'll see the difference. Let's just say 200 points I'll give. Okay, access 3D. Okay, now it changed a little bit. Here it became yellow, it became upper here. Earlier there was 6, that 6 is gone. So okay, instead of 200, let me change the value here also. Now this equation is two random values are initialized for m and one value is added. Let me make it 3. So slightly I'm modifying just to show you what the cost function looks like. Okay, 1 second. Fine, let me make it m, but I will change the equation here. Okay, now see, it tilted, it went in different direction. Okay, now you can see 7 here. Upper point is here. Clearly you have to go in this direction to the lowest point wherever it is in this cost function. Okay, you can even add few more points if you want. Okay, few more points hasn't changed, but anyway you get the idea, right? So you can change the equation. Let me make it like 15x or even -3. You can, okay, -3 means the entire cost function area changed. So it went like this to this. Actually, if you change it, I don't know if I can change it. If I don't know if I can rotate it. If you rotate it, you can see S shape actually. Okay, it's gone, like from here to here, it's gone. But you are seeing it from the right side. That's why you are unable to understand. But anyway, the point I'm trying to make is, The cost function that you calculate, that is injected into this Hessian matrix. You will get that local maxima and minima, okay, which looks something like this. Okay, now, so those things are here. One of the method is Newton-Raphson, which is what it does. It calculates the maximum and minima by making use of this Hessian matrix. And once you know that maxima and minima, now you know which direction to go to. Okay, that means your slope, m is slope here, theta is slope. Okay, this theta and m are 1. So in order to take the next step, you know from the uppermost point, you have to subtract in order to go to the lowermost point. Okay, so that is done by making use of this inverse of Hessian matrix. H inverse is calculated, which is multiplied to the gradient of log likelihood function that we saw. So that to that function it is multiplied, and when you multiply it, it automatically starts taking the steps. That also I'll show you, but I'm just explaining. So take the Hessian matrix, get the 2 points, upper point and lower point. Once you have those points, from that point, okay, by taking the inverse of Hessian matrix, multiply it with to the change gradient of slope, and that term you have to subtract from the original slope, thereby decreasing the slope. When you decrease the slope, m value decreases, and when m value decreases, because you are multiplying m with y value, x value, your y prediction also decreases. If y prediction decreases, it goes very nearer to y, original y. Okay, so this way each one is dependent. So basically Hessian matrix will help us in giving the curvature of the loss function, and using these 2 points we are converging. And how are we converging? By multiplying small term to the gradient. Gradient means your learning parameter. Learning parameter is being multiplied to the change of slope. Okay, so this is how Hessian matrix is helping. Is this clear? I mean, there are research papers if you want to learn completely step by step, end to end, but I don't think that much would be necessary. But I have attached certain links. Okay, so you can go through the links to understand how Hessian matrix are being used. Okay, so here everything is there. How Hessian matrix is calculating, all those determinants are being used. How is this determinant looking? For example, for this one, as you can see, it looks on a 2D plane like this. You have to, basically our aim is to go from this line to this line, this line to this line. So at the line which has the which is very closer to 0 on the x value, you have to go to that line. So till here, so how much step to take is determined by the difference of these points. Okay, so this way it is used. You can go through all these if you like, if you are interested, but the algorithm solver is using this Hessian matrix. Okay, so cost function looks like this. Let me put it to a positive value. Yeah, looks like this. Okay, so I have applied the same thing here. By default, if you don't specify the solver, by default solver is LBFGS, and we will see how that works, but initially we saw Newton-Raphson. Okay, finally the decision boundary gets drawn like this. Okay, this is all done by model, you don't have to worry, manually draw. It segregates the decision boundary. Next is, what are the different solvers available, for which model we have to use which one. Okay, LBFGS can be used for multinomial. Okay, and it can also be used for binary classification with L2 penalty. L1 penalty is not available for LBFGS. Liblinear is L1, L2 is applicable, but it is only for binary classification. Newton CG, Newton Cholsky, so these are applicable for binary. Okay, one of them is applicable for multinomial. Okay, for with L2 regularization. Same way Saga and SAG. SAG and Saga are stochastic gradient descents. Next, let's look at what is LBFGS. LBFGS stands for, you just understand, limited memory. That much you remember. Rest are the names of the scientists who came up with this. limited memory means it is a solver that uses very least amount of memory, and it is best suited for large number of parameters. Okay, and it can be used to find out m values. Theta means m, remember, it is used for finding out the m values. So initially how it works is you start with initial estimates of model, okay, and then you approximate by using inverse Hessian matrix. First you don't know what is the m value, you randomly initialized. Okay, let's just say you don't know m values. M values could be anywhere on this plot. Okay, m values could be any point on this graph, whatever the area. It could be here, it could be here, it could be here, it could be here, it could be here. Randomly initialized, right? So it would be random value. First, once it is a random value, random point, second thing is you will get to know maxima and minima, and from that point, randomly initialized point, you know the minima value. To which value you have to arrive, you already know. So you will start minimizing. Basically, you will start iteratively minimizing that cost function, which is negative livelihood, okay, by doing the following steps, what you are going to see here. Okay, what are those steps? What you will do is, you will take that m value, theta is m value, to that m value, you already have x, we already have x, you will do this subtraction. You will do this subtraction, x into theta you will take, y was the original value, sigma of x into theta you will take, you will subtract and then multiply into x. So basically what essentially you are doing is, let's just say y was 5. Okay, after calculating this became 4. 5 minus 4 is 1. Okay, so you are multiplying 1 to x of t. So basically the point, okay, let's just say this was 5.5, this was 4, 1.5 difference you got here, you're multiplying 1.5 here. Okay, so that is how change in theta is being calculated. Okay, next step is updating the parameters. How do you update the parameter? By again, so again that you will do for, in order to take the next step in the theta, okay, what you will do is you will subtract the Hessian matrix inverse with theta. One, you are calculating how much to change, make the change, whatever the value you get here, that much change you will take in the randomly initialized m values. Okay, these changes are happening to m only. We call it slope gradient. Okay, next, how much to take the step you calculated. Okay, in which direction to take, that you will calculate by making use of this Hessian matrix multiplied with whatever the theta you calculate. You calculated the difference here, no? That only you are going to multiply here with the inverse of matrix. This subtraction term is done to the slope. So thereby you are reducing the slope here. Okay, here you calculated how much to take, how much the change happened, and that change you are subtracting to original theta. Okay, so thereby you are taking the next step to the slope, which is decreasing the slope basically. Okay, I mean, don't worry about the complex equations, you don't have to remember these, but just understand the flow. Once you understand this, your entire deep learning will become easy. Okay, next is Hessian matrix. After you do this, after you took the next step, you're gonna repeat the same step multiple times. That's why it says iteratively. Multiple times you will repeat the step until the convergence happens. Convergence means you arrive at the minima value. No, you have equated the change the value to the minima. Until that point you will keep on changing this cost function. Okay, or one, either you reach the minima or you have reached the number of iterations. Initial iteration you gave as 100 times you have to do this process, bolke. So 100 times you will do and stop. Either you do that or 30 times only you will do until the cost function comes, converges. Okay, so this method is memory efficient, and can be used for large scale problems. Okay, and it has fast convergence rate also, hence it is scalable. So when you use logistic regression, if you want to deploy it in production, ensure that your solver is LBFGS. Don't go on to randomly choose any solver, otherwise it won't be scalable. Otherwise again you'll have to do the retraining. Your model will show concept drift. Okay, data, there are certain things like data drift, concept drift, and there are few other drifts also. Okay, feature drift we call it. So I think MLOps folks will be already aware of this. So concept drift will happen. Your model will no longer will be applicable for the new data if you don't do this. Okay, make sure the solver is LBFGS. Okay, understood till here? Okay, okay, fine, thank you. So next step is, okay, next thing is, by default solver is LBFGS. That is the good thing for you. Okay, sometimes you might forget, but by default it is chosen. So I have applied this LBFGS and tried to calculate the decision, shown the features here and tried to calculate the decision boundary, how it is trying to separate it out. It is a lot of things are happening which are not displayed. All you have to understand with this graph is that how it is able to segregate the data. It is not applying, it has applied sigmoid already, which is not being seen here, but you are only seeing the decision boundary, how it is segregating. This is don't get confused this with this is different. This is not what I'm showing here. What I'm showing here you is the segregation of the decision boundary only. Okay, all right, next solver is next solver is liblinear. Okay, this is what happens. So after you get the y-pred values, you apply the sigmoid function. They either get aligned on the upper axis or they get aligned on the lower axis, or sometimes they even come in the middle. That's why you have threshold. Any point above threshold, you will classify these as one class, this as second class. Anyway, liblinear is another popular choice, and this can be used for large scale data sets. Okay, now what liblinear is doing is, it works little differently. It uses this function. Okay, it takes the slope, to that it is calculating some transpose of, anyway slope is a matrix, right? M is nothing but M1, it's a matrix of M1, M2, M3, etc. So to that it's transposing, multiplying it with M again, plus it's doing some log complex calculation. Okay, so we call it logistic loss. Whatever the outcome of this is, we call it logistic loss function. So what liblinear is doing is, basically it is making use of regularization, L2 regularization. Okay, and underneath it makes use of something called crescent descent. Now crescent descent method, okay, it iteratively optimizes or iteratively updates one parameter at a time. This is the difference, while keeping others fixed. Basically crescent descent, if it is optimizing theta value, it won't touch c value, okay, or theta naught value. So it alters one parameter while keeping other. For example, if in your model you pass the liblinear method and you also specified what is a regularization parameter, you specified learning parameter, you specified many others. So what this method does is, it changes one parameter, keeps everything constant, and tries to measure how much change is happening. Then it keeps the other one, the first one as fixed, changes the rest of the ones, and calculates how much the change is happening, how much cost function is decreasing. Okay, how much it is able to optimize the value of m. So that is being measured. This is how liblinear works. Okay, here I have too much explanation also, but for you, if you want to in a simple way understand, there are multiple parameters. Okay, here model parameters are theta, indicated by theta, and C is a regularization parameter. You have Y label also, you have X input features vectors also. So what this liblinear does is it will modify this and it will keep rest of the things as constant. Then it will keep rest of the things as constant and modify this. Then it will keep this as a constant and then modify this. Okay, this way one it is altering. Okay, it will change one by one. It will keep one fixed and the other modify and thereby see how much difference can be arrived. So this way it calculates. Okay, the advantage is it's computationally efficient. If you want to do the training on a lot of data, then you can use liblinear. Okay, some of the I will explain coordinate descent in detail how it works, but underneath it is using the coordinate descent and Newton methods. Okay, so one more thing I forgot to tell you is it basically uses two things: coordinate descent and trust region. The primary one is coordinate descent. If using coordinate descent it is unable to solve the problem, it will make use of the Newton method. It keeps switching between the two. Okay, so that much you remember for now. Okay, in the trust region, okay, basically there is another method, right? One is coordinate descent, another one is a Newton method. In Newton method, what it is doing is it is initializing the parameters alpha mainly, okay, and calculating the gradient descent by making use of Hessian matrix. So first way, see, two different methods it uses. First is coordinate descent. Coordinate descent I'll explain you. Okay, but the second method is Newton method. Now Newton method uses Hessian matrix. First it will try with coordinate descent. If it is able to solve, well and good. If not, it will switch to Newton method. And in Newton method, you already know what happens. All the things that we saw above will repeat. Okay. So this way, that's why we call it dual problem formulation. Okay. Because two different methods are being used to solve the problem. Okay. Dual formulation. Because it uses dual formulation, if there are too many columns in your data set, this method can handle those high dimensional features. Hence, if you have too much columns and if you want to use logistic regression, then you have to use liblinear. Don't use LBFGS, because computationally efficient method is this one, not that. Okay. So this way you can choose between liblinear and LBFGS. So basically coordinate descent, what it does is it's very similar to gradient descent. Okay, let me open here. I think I had the link. I lost the link for gradient descent. So there is a minor difference between the two. Which one you should choose and how to choose and all. I think not this link. One moment. Not this. I think I had one good one, or maybe I have added here in the somewhere. Okay, there is a minor difference. Okay, this is what the coordinate descent looks like. Okay, so it's a descent path, coordinate descent path, how it is able to arrive. Initially it started here. It started here at this point. It adjusted. See the learning parameter, the distance between these 2 points is the difference in the slope. It jumped from here to here. Okay, then here, then here. So basically the iteratively it decreased the values of m. Okay, but that's not how gradient descent works. Gradient descent has a constant learning rate. Here In crescent descent, you have a variable learning rate. It keeps on decreases, okay, and thereby slope also decreases. Uh, Gradient descent, okay, anyway, okay, I will pull the differences and explain you one. I think gradient descent. Okay, yeah. So this is one difference. You are no longer calculating the derivatives for gradient descent. That in itself saves a lot of computation. Okay, that is one difference. Second thing is steep means lowest point. Gradient descent moves in the direction of steepest descent. Okay, whereas coordinate descent, it only looks for the minimum of that function. Okay, and it moves in that direction. So for gradient descent, it has to move in the direction of steepest descent. That means if your theta value, for every step you are calculating the gradient in gradient descent, that is a difference in the theta values, and accordingly moving. So your direction is not linear, it is switching left right and all of that in gradient descent from one point to another point. But in crescent descent, that's not the case. Okay, mostly that's why you can see it's more or less in the straight line only. More or less it's in the straight line. It has moved. It's because it's not, it doesn't care from, it doesn't go from here to here and then here, then here, then here, like that. In zigzag way it doesn't go, it goes in a straight line only. That is another. Okay, and gradient descent, yeah, they have given one simple example. Gradient descent is nothing but you throw a ball, you roll a ball, not throw, roll a ball down the hill, okay, until it reaches the bottom. So sometimes the ball can, basis on the wherever the portion is down, it can go in that direction. Ultimately it will reach the bottom, but it will go left, right and all of that and reach it. Okay, whereas gradient crescent descent is not like that. So it is like someone starts at the corner of the city and follows the path in the grid pattern. That means straight line it is going. Okay, so that way you can understand. But anyway, I will. This is not the complete list. I lodge the link. I will fetch you the complete details and explain you in a bit. Okay, bit by bit how it works. What is the difference between gradient descent and coordinate descent? But coordinate descent is, it also does 90% similar to what gradient descent does. Okay, 90% is same. If you look at the function here and understand, okay, it is also taking, basically it is also taking the matrix, okay, and it is calculating the sigmoid, it is subtracting the learning rate by multiplying with gradient, okay, and it is calculating the path. So 90% of what it is doing is similar except for this sigmoid part. Okay, you don't have sigmoid in the gradient descent function. In gradient descent function, there is only calculation of matrix by and subtracting the learning rate into gradient. That much you have, but you don't have this sigmoid portion. Okay, so I think this is the difference in coordinate descent and gradient descent. So basically you can see how it is moving. Okay, so this is what liblinear is. Liblinear you have to use when you have too many columns. Okay, this way I mean this is just the indication of loss function. For various iterations, loss function has decreased, which is good. We want loss function to be lower. Okay, if loss function is lower, our accuracy will be higher. And here we are showing precision recall. I will talk about metrics, okay, evaluation metrics, and I will explain them in depth. But for now, we are still in solvers only. Okay, that did you get basic things about liblinear? Okay, so liblinear, just understand it switches between two different things. One is coordinate descent, okay, and coordinate descent also does the same thing, same as very gradient descent, except for the sigmoid portion section. Next is, if it is unable to get the result using coordinate descent, it will switch to Hessian matrix calculation. Okay, two different, that's why we call it as dual formulation. For single problem you have two different solutions, that is why we call dual formulation with liblinear. And the difference is LBFGS you can use it if you want to have lower memory, if your compute is lower, is you want to have it has low memory. Okay, if your business says we want to deploy this model with least memory and least computation possible, go with the LBFGS. But at the same time you see there are a lot of columns, then switch to LBFGS, sorry, liblinear. Okay, so basis on this you take the call. Okay, and you have to give the same message to data scientists who are training the model if you are the person who is going to deploy the model. Anyway, so this is all about the concepts on logistic regression, and next we have to see the problem itself. Okay, so I want to stop it here. Tomorrow we will see the classification of logistic regression, and we will see one regression problem on logistic regression, and then we will complete it.